Let's look now at section 14.6 and talk about triple integrals. In the previous section, we talked about the surface area of a three-dimensional surface. Now we're going to be looking at volume within that surface. The difference being, up to now we've had something that was hollow. We've been looking at just the outer skin of this. And we've either been saying at each point of the skin, we're going to take a value. Right? That value isn't usually something that we worry about. We don't worry about the application, but it could be the temperature at this point. It could be the electricity running through this point. It could be the mass at this point, whatever. And at every one of these points, and here's a point, right? At every one of these points, I can give that value, and if I add them all together, that's my that's my integral, right? I in the last section did that with surface area by saying, oh, I can break this into little tiny pieces, find the area of each of these pieces, and put them together. The difference is now, instead of looking at a surface, what we're going to be looking at is not just the surface, but the material inside. So we're going to fill this in, and we're going to be looking at not only the material on the outside, but also the stuff inside as well, right? So now we're going to be looking at a three-dimensional object, something solid that's closed off on all sides, and that inside has some material. So now 2 dimensions are no longer enough. Now we're going to be looking at something like this. Here, I'm not going to be developing the theory the way I did in previous sections for 2 reasons. One, the way I developed it was using some illustrations. We develop an intuition as to how do we start from a general approximation to get an exact value going through the limit. I'm a little bit limited here in that I can't really draw some of these objects. Some of these things are going to be 4-dimensional objects with a 3-dimensional domain. So the illustrations aren't really feasible. The other thing, though, is even without the illustrations, if we go through and do just the analysis, just the notation, you'll find that it's very, very similar to what we've done before, where essentially we approximate one object with a simpler object, add those simpler objects together over the region that we care about. In previous sections, we saw this was delta A, now it's delta V. Before we were talking about a flat area, now we're talking over a volume. But aside from those changes in dimension, the notation and the development of that notation turns out to be exactly the same. So here, instead of going through all of that, let's go ahead and give our definition and our theorem because it does reflect most of what we've seen in previous sections with the double integral. So definition. Let f of x comma y comma z. Now we have 3 variables for our domain, which means our function is a 4th-dimensional object, 3 domain and 1 for its range. Let f of x comma y comma z be a function that is continuous over a bounded solid region Q. Remember, it's bounded and solid. It's not just the outer area, but the stuff inside as well. This object is called the triple integral of f over q. It's denoted with 3 integrals with a q, and that'll be a solid region, which will define our domain. Here's your function, which you're integrating over this region, and it's all with respect to volume, as opposed to area for the double integral. All right? That's going to be defined as the limit, assuming that this limit exists, as the norm of our partition approaches 0 of the sum of the function times delta vi. Right? And again, the name for this notation is the triple integral of f over q. Just like we could find the area of a surface by taking its double integral with respect to area, we'll be able to find the volume of a solid by taking its triple integral over the differential of volume. So before we saw double integral over r dA is area. Now we see triple integral over q dV is volume. The result is different, the number of dimensions is different, but the development is the same. Now, the theorem that allows us to evaluate this simply is reminiscent to Fubini's theorem. In fact, it's an extension of Fubini's theorem. It says, let f of x comma y comma z be a function that is continuous on a solid region Q. So you have your x, y, z coordinate system. There's some object we call Q that works as our domain, and the function is continuous over that domain. Now that domain is going to be defined as follows. One of the variables is bounded by functions of the other two. Now here we write it as x and then y and then z. You could have done it in any order. You could have started with z and then x and then y. We'll see that as we go through some examples that our boundaries of integration can be changed around a bit. But without too much loss of generality here, we can say, okay, this variable is bounded by functions of the other two variables. Okay, this variable, and I've made a mistake here. That is not correct. There we go. This variable is bounded by functions of only this variable. So notice, this one can be bounded by either of these. This one can only be bounded by this one. And this one should only be bounded by constants. What that means is one variable can depend on the other two. Another variable should only depend on one of the other ones. And a third variable should not depend on any other variables. It should only be bounded by constants. Here, it doesn't have to be x and y and z in that order, but in some order, you have to have one variable dependent on the other two, one dependent on only one other one, and one that's only dependent on constants. Here, these h and g functions that bound two of our variables should be continuous. They don't have to be anything in particular as long as they're continuous. Okay? So if you have a function defined over a region Q that's defined this way, then the triple integral over Q of f dv is given by a triple integral. All right? That makes some bit of sense. A double integral was evaluated as a doubly iterated integral. Now a triple integral will be evaluated as a triply iterated integral of f of x. Here, z goes first, and it's bound by these functions. Then y is bound by these functions. And finally, your last variable should only be bound by constants. Note, this one can depend on either of those. This one can only depend on that one. And this one shouldn't depend on anything but constants. Right? Starting from the inside out, this can depend on all of those. This can only depend on the one you haven't used yet. And this can only depend on, well, nothing else, just constants. So let's take a look at an example, actually several examples of how we want to use this. So let's begin with just evaluate a triple integral. Okay? Let's evaluate the triple integral given by the integral from 0 to pi over 2, of the integral from 0 to y over 2, of the integral of 0 to 1 over y, of sine of y, dz, dx, dy. So now this is the first triply iterated integral you've ever seen in this course. However, it's not any different from a doubly iterated integral. You start from the inside, integrate, and then once you have that result, you integrate again. And once you have that result, you'll integrate a third time. So you might want to try this. Go ahead and pause the video and see if you can get through all three integrals. Once you're done, your result should be a constant. You should get some number like 5 or something like that, because after all, your boundaries of integration at the end are constant. So pause the video, give that a try, and whenever you have a result, go ahead and unpause and we'll go through it together. All right, so the first part of the integral seems nice and straightforward. After all, sine of y is a constant with respect to z. So this first integral here is simply the integral of a constant dz, which is just that constant times z. So that's integral from 0 to pi over 2 of the integral from 0 to y over 2 of sine of y times z. And here we're going to take z from 0 up to z equals 1 over y. dy, dx dy, just like that. Okay. Now here, note that I write z is equal to, because as you start having multiple integrals, sometimes the orders of these will be different, z, y, x, z, x, y, or some other combination, and it's really easy to lose track of what you're trying to plug in here. So you'll notice that I have a habit of writing out what variable I'm about to plug in for. So here we go. Obviously, sine of y times 0 is 0, so we don't worry about that one. But this one is going to be, well, it's the integral from 0 to pi over 2 of the integral from 0 to y over 2 of, well, that's just sine of y times 1 over y, or more simply, sine of y over y. Dx dy. Okay. The next integral is also reasonably simple because, again, this is a constant with respect to this variable. There is no x here. So to take this integral, I'm simply going to take this constant times x. So that'll be the integral from 0 to pi over 2 of sine of y over y times x. And here we're evaluating this from wherever x is equal to 0. My variable of integration is x, so I'm evaluating where x is equal to 0 up to wherever x is equal to y over 2. Now, since x is equal to 0 here, anything times 0 is 0, so we don't worry about that. But now, if you evaluate where x is equal to y over 2, this will give us the integral from 0 to pi over 2 of the sine of y over y times, well, x is now y over 2, dy like this. Right. Sine of y over y. X is now equal to y over 2, so that's what's being multiplied. And here these simply divide away. Here that's a constant, 1/2, so I can go ahead and pull that out. So that'll give me 1/2 the integral from 0 to pi over 2 of the sine of y dy. And that's a nice antiderivative to take. That's simply negative the cosine of y. Now we have a 1/2 out here, so we can write this as negative 1/2 the cosine of y evaluated from 0 up to pi over 2. Well, I know the cosine of pi over 2 is equal to 0, so that's going to equal to negative 1/2 times, well, that's going to be 0. The cosine of 0 is 1, and I'm subtracting those. So that'll give me negative 1/2 times negative 1, which is simply 1/2. Just like that. So the result of our triple integral, our triply iterated integral is 1/2. Now, for our next example, what we want to see is what happens when we have to set up our own. We've seen this in previous sections where we set up our own double integral based off of some region in the xy plane. So our next problem is going to read, so example, set up. Here they're being nice to us. They're not asking us to actually go through and perform the triple integral, partially because some of these are simple and some of them are complicated. And here they just want us to practice the actual setup. In some of the later problems, we'll actually go through the entire problem. But this one just has us setting something up. So set up the triple integral to evaluate the volume of the solid bound by the following functions. Let's see, the functions that we have, it's going to be bounded above by z equals to 4 minus x squared above, and z equals x squared plus 3y squared below. So note that in the definition, we also saw that a triple integral can be used to evaluate the volume by taking the triple integral of the differential of volume. All right? So here, as long as we can describe Q adequately, the triple integral dV will give us that result. All right, so that's what this is saying. It's saying, okay, we want V to equal the triple integral over Q of dV. And now we simply need to describe this as a triple integral given the following boundaries. Now, while a sketch of this is not at all required or necessary for the purposes of this first explanation, I'm going to go ahead and give a crude illustration, and I do mean crude here. Let's see. Let's take... And you know what? This might take me a few moments to set up, so I'm going to go ahead and pause my video, and then from your point of view, it'll be an instantaneous drawing, all right? And here we are. We have a cylinder. Notice this is missing the y variable, so this would be this would have rulings that are parallel to the y-axis. So here's your x, and here's your y. So your rulings are parallel to the y-axis. Notice that the generating curve is simply a parabola, y minus x squared. 4 minus x squared. And so that's a parabola that faces downwards. All right, so we have a generating curve that's a parabola facing downwards, and then the rulings are parallel to the y-axis. So you have this sort of orange, like a tunnel. Now we want things that are above that and that are below this surface here, which is a paraboloid. Notice if I look at my xz trace, that's a parabola. My yz trace is also a parabola, so I have parabolas in both directions. And here, these cross sections, these level curves, would be ellipses. Right? They're almost a circle, but one has a higher coefficient than the other, which gives you some form of eccentricity. So we have these two shapes here, and since this is, you're bounded by this below, that means that that purple one is the lowest part. Since you're bounded by this above, well, then that means the orange one is the highest part. So that means that the region that we want is all the stuff in between here, all the stuff that's below the orange and above the purple, stuff in there. Which may not be the most visually appealing illustration, but hopefully it drives across what we're trying to get. We're trying to get all the stuff that's bounded below by the purple paraboloid and that's bounded above by the cylinder. So all the stuff in between them. Okay, so now we can go ahead and describe this as a triple integral. And because of our extended version of Fubini's theorem, we can now write this as a triply iterated integral of dV. Okay, so now here we're going to say, okay, dV can be written in terms of the three variables of integration, x and y and z. It doesn't actually matter which way they're oriented. We'll see here in a few examples that you can actually even change the order of integration, just like you could with a double integral. So here we can do x then y then z, or y then z then x, or any other combination. But I noticed that right away I have my boundaries for z. They're already given to me. I have the upper and the lower bounds, right? I'm bounded above by this and below by this. Oh, okay, so I may as well start with those. So here my dv, I'm going to write that as dz, and then the other two, I'll just go ahead and pick. I'll say dy and dx. Once again, I'm starting with this because here I already know my boundaries of z. Not only that, but remember from our theorem that your function that bounds one of your variables will involve two other variables. So if you had a function of x and z, it would bound y. Or if you had a function of z and y, it would bound x. Or in this case, if you have a function of y and x, it will bound z. But notice that's the only one that can be bound by two variables. All the other ones can be bound by either one or no variables, by only constants. So that means that the very first variable that we consider will be the one that's bounded by up to 2 variables. And since here my two surfaces involve both variables x and y, or at least this one does, we really don't want to mess that up. We really don't want to have to worry about, oh, can I redefine this using fewer variables? So here, my z is bound by two functions of x and y. It's bounded below by this, so that's going to be x squared plus 3y squared. And it's bounded above by this, which is 4 minus x squared. Okay. Now, this one can only be bound by the variable we haven't looked at yet. All right? Here, we've already seen z. So this one can't be bounded by z anymore. It can only be bounded by the variables we haven't looked at yet. Since we're currently looking at y, well, you can't bound y with itself. So this should only be bounded using the x variable. And then these should only have constants. All right. So now let's see what that's going to look like. Well, notice when you have your surface, that's your two surfaces rather, that are bounding this solid, those two surfaces are going to cross somewhere. Those two surfaces are going to have a curve of intersection. Oh, well, that curve of intersection will tell me the boundaries. It'll tell me how far out each of these surfaces go when they run into each other. So here, let's consider the curve of intersection of these two surfaces. Okay, let me do that down here. Consider the curve of intersection of our surfaces. Okay, well, that's pretty straightforward. Z is equal to this and z is equal to that. So if they're intersecting, well, this z should be equal to that z, which makes this expression equal to that expression. It's just like back in basic algebra. Where do two things intersect? Well, let's set them equal to each other and see what happens. So that's going to be 4 minus x squared is equal to x squared plus 3y squared. Notice this is what we want. We're trying to describe these using only the remaining variables, no more x. And that's precisely what we have here. Here I'm trying to describe y in particular. So here let me try to isolate my y. If I subtract x squared over this way, that's going to give me 4 minus double x squared is equal to 3y squared. And then I can go ahead and divide both sides by 3, and that'll give me y squared is equal to 4 minus 2x squared over 3. When I take the square root, I'm going to get my upper and my lower boundaries. You say, well, there's only one equation. Right, but I'm taking a square root, which will give me plus and minus. Right? Here it seems pretty apparent that y takes on positive values, but also negative values, just from the illustration here. So when I take the square root, I get y equals plus or minus the square root of 4 minus 2x squared over 3, which means that my upper boundary will be the positive square root of 4 minus 2x squared over 3. And the lower bound should be the negative square root thereof, 4 minus 2x squared over 3. And finally, we need to describe x. And here x needs to be described using only constants. And there's a few ways you might think about that. One way is to just look at this and realize, oh, this is a radical. It's only defined as long as the stuff inside is positive. So that's one way we could figure out what x is. Say, okay, well, let's make this whole thing positive. Another way to do that is maybe a little simpler, or at least a little more intuitive. It's a little more visual. Here, instead of isolating my y, go back to our original curve of intersection and look, add the x squared over this way. Instead of bringing it over here to isolate your y, let's bring it back this way. That's going to give us 2x squared, since I've added it to this side, plus 3y squared is equal to 4. That's an ellipse. And this ellipse we can find its extremities. We can find the points that are furthest away from the origin. Notice that's an ellipse centered at the origin. By simply saying, okay, well, if that one's equal to 0, what does the other one have to equal to? Okay, well, if that one's equal to 0, what does the other one have to equal to? Here, we only care about x, so let's just do that one. Here we would say, okay, if y is equal to 0, how far out does x need to go? Well, I could divide both sides by 2. X squared is equal to positive 2. And then if x squared is equal to positive 2, I could take the square root of both sides, and I would get positive root 2, and I would get negative root 2. We can do the same thing for this one. It's not really necessary, but we could. Divide both sides by 3, take the square root, and we would get the square root of 4/3 and negative square root of 4/3. And that's the curve at which those two intersect. But again, we didn't need the whole curve. Here, we just need these outer boundaries, because here that's what describes x. All right. Oh, okay. So now I know that x goes from negative root 2 to positive root 2. And up here, that must be negative root 2 and positive root 2 as my boundaries of integration. And there we go. That's all set up. And that's what we were after. The volume would be given by the triple integral of negative root 2 to root 2 of the integral of negative root 4 minus 2x squared over 3 to positive root 4 over 2x squared over 3 of the integral from x squared plus 3y squared to 4 minus x squared dz dy dx. Just like that. So now, let's have you try one. This one will go all the way through. This one will have you first set it up, and then once it's set up, go ahead and perform the integral. So far, we split that into 2 problems. This one, we just set it up and stopped. In this other one, we had something that was already set up and we went all the way through. Here, we're going to do both. So you're going to go ahead and try this one. Find the volume. Of the solid that is bound by z equals to x, y equals to x plus 2, and y equals x squared, all in octant 1. Now remember, octant number 1 just means x and y and z are all positive. Octant number 1 just means x is greater or equal to 0, y is greater or equal to 0, and z is greater or equal to 0. That's all octant 1 means. So go ahead and give that a try. This is a 2-stage problem. You're going to first set up the triple integral, and then you're going to complete the triple integral to give the volume of the solid region. Go ahead and pause the video, give it a try, and when you get an answer, go ahead and unpause, and we'll do it together. All right, so if we're going to find the volume, first we need to be able to describe this region so that we can develop the boundaries of our triple integral. So let's go ahead and start off. I'm going to make a crude sketch of just the basics of these boundaries. First of all, I notice both of these are with respect to just x and y, and that's nice. So let me go ahead and start by drawing these because they'll interact together nicely. Here, let me adjust on the xy plane. I have the line y equals to x squared. So here's my x and here's my y, and that's just a parabola. That looks like that. And then over here I have y equals to x plus 2, which is the equation, the linear equation of slope 1 with a y-intercept of 0, 2. So it'll be up here, and it'll have a slope of 1. So let's see, let's make this all uniform. 1, 2, something like this. Okay. Okay, so this is the line y equals to x plus 2. I have 0, 2 as my y-intercept, and then my slope is 1. So up 1 over 1, up 1 over 1, like that. All right, so those are my two lines. I have y equals x plus 2 and y equals x squared, and I want the things that are bounded by those. Oh, but we also want things in octant number 1. And in octant number 1, everything is positive. So what I really want is all of this stuff right here. Here I have the point 0, 0. Here I have the point 0, 2. And here I have the point 2, comma 4. All right. After all, that was where these two intersect. So 2, comma 4. All right. Now, if I take this object, I can use that as the starting basis, literally the basis on the xy plane of my solid region. And here, let me take this away, and for you, it'll be an instantaneous drawing here. And it would essentially generate something that looks like this. Note that since this is completely independent of the z variable, you could consider this as being a cylinder, or at least this outer set of curves, you could consider them being a cylinder. So this outer set of curves would be this outer set of curves, and that would generate a cylinder that would have rulings parallel to the z-axis. So we'd have this object here. Now, we haven't used this one at all, and in order to keep the drawing from getting too cluttered to the point of not being intelligible, I'm not going to draw in that third component. But note that you're simply saying, well, that's the height of your function. This has no restrictions on height at all. It just keeps going up forever. All right? But here, this gives you a restriction on z. So that's simply giving you the upper bound on z. Clearly, the lower bound is the xy plane, because of course we want to be in the first octant. We can't have z be anything negative. So our lower bound must be 0, and this must be our upper bound. So here, let's just use this to help us find the rest of our bounds. Yeah. So let's set up our triple integral. Here, our volume is going to be the triple integral over the region Q of dv, like this, which by our theorem is given by the triply iterated integral. And here dv, we're going to write it as dx dy dz or something of that nature. Here, we already noted that z is simple enough to talk about. Here, we're going to go ahead and take this and treat it as the upper bound of our solid. This wouldn't have any upper bounds. It's a cylinder. It continues up forever. So clearly that must be the upper bound, since it's the only bound on z that we could ever find. The lower bound is, well, got to be 0, because we want to be in octant number 1. So here, we're going to start off with dz, and that's going to go from a low of 0 to a high of x. Here, we want to describe z using a function of x and y. You say, well, I don't have a y there. Oh, that's fine. By default, you would just say, well, you could think of this as x plus 0y, if need be. So here, it doesn't mean that you need both of them. Just by default, you can have up to both of them. So this is still acceptable. Now let's go ahead and take the other ones. Here, this is the same as this. So you can either look here or here to find the boundaries. And here I'll do this with respect to y and with respect to z, with respect to x, like this. I would rather not use x first, because if I look right here, this has a left boundary for x, and this is the right boundary for x. Well, yeah, that's only true until I get right here. And then this is now the left boundary of x, and this is the right boundary of x. So if I'm describing x using variables, well, I have to do it 2 different times, which means I have to take this object and split it into 2 regions. I'd have to come over here and say, okay, here's region 1, here's region 2, and I'm going to need to integrate 2 different times. And that just sounds like it's more trouble than it's worth. But if I start with y first, oh, okay, well, y is not so bad, because y always goes from this curve up to this line, from bottom to top. and it only has one lower bound and one upper bound, so here we won't need to split our integral two different ways. So here the lower bound is this parabola, y is equal to x squared. The upper bound for y is this straight line, where y is equal to x plus 2. So again, y is equal to x plus 2. And finally, x needs to be described using only constants, which makes it simple. Here, the furthest left x anywhere ever gets anywhere is going to be 0. But the furthest right gets, well, you say, well, that's this curve. No, just as a constant. The furthest single point that you ever get to, oh, that's right here. That's at 2. So it's going to go from 0 up to 2. And this is our setup. This is going to give us our volume. So now we need to evaluate this volume. Okay? If you hadn't gotten to the end of the problem, you might, if you got stuck setting up the integral, maybe you want to try it now. You could take the opportunity to pause the video, and once you finish evaluating this, then you can unpause and we'll go through it together. All right, so let's go ahead and integrate. We're starting off from the innermost set of integrations and working our way out. Here, we're integrating with respect to z. Here, if you think, well, there's nothing there, well, you can think of it as 1 if you like. And so that's going to be just 1z evaluated from 0 up to x. So here, that's going to be the integral from 0 to 2 of the integral of x squared up to x plus 2 of z evaluated from where z is equal to 0 up to where z is equal to x. dy dx. Just like that. But now here, if I evaluate this, that's just x, and here that would be 0. So we don't worry about that one. And we're simply left with the integral from 0 to 2 of the integral from x squared up to x plus 2 of x dy dx. So now I take the next integral, and I'm integrating x with respect to y. Well, with respect to y, x is constant, so the integral would just be x times y. So this will give us the integral from 0 to 2 of xy. And now here, our y value is going to equal to x squared up to where our y value is equal to x plus 2. Like that. Now here we can evaluate at either endpoint and subtract. So if we substitute in x plus 2 for y, this is now equal to the integral from 0 to 2 of, I'm still looking at just the stuff in these brackets. That's going to be x times x plus 2, which is x squared plus 2x. Oops, plus 2x. I'm not sure why I decided that needed to be exponential. X squared plus 2x minus, and then if we take this one and plug in right here, that's going to be x times x squared is x to the third dx. So evaluating those gives us this, and now we have one last integral to evaluate. Here, let me write this on a fresh line. That's going to be the integral from 0 to 2 of 2x. I'm going to put it in ascending order, just because. Like that. And now I can use the power rule on this, and we're back in Cal 1. So this is now the antiderivative of 2x with respect to x. Well, that's going to be x squared. The antiderivative of x squared with respect to x. Well, that's going to be plus x to the third over 3. Minus the antiderivative of x to the third with respect to x is x to the fourth over 4. And we're evaluating that from x equals to 0 up to x equals to 2. Well, now if x is equal to 0, then that's just 0 plus 0 minus 0. So that's all 0. This one is irrelevant to us. So all that really matters is this upper bound, which is going to be 2 to the second power plus 2 to the third power over 3 minus 2 to the fourth power over 4. Evaluating this at 2, at 2, and at 2. Evaluating at 0 gives you 0, so we don't worry about that one. So that's going to be 4 plus 8/3 minus 4 squared. That's 16 over 4. And you'll notice that 4 minus 4 minus 4, well, that's just 0. So in the end, the volume of the solid that was described above, the volume of the solid bound by these in octet number 1, is simply 8/3. Just like that. Find the volume bound by this. Here, let me write that 8/3. And that way it all fits on 1. Okay, so now the last part of this section, let's take a look at changing boundaries of integration. We've seen how to change boundaries of integration in previous sections for regions in the plane. The same thing can be done for a solid in the XYZ coordinate system, but we have to be just a little bit more careful, and it does take a bit more methodology to do it. The idea is still the same, but it does just take a bit more care. So let's consider the problem example here. Let's go ahead and take this one, integral from 0 to 2 of the integral from 2x up to 4 of the integral from 0 to the square root of y squared minus 4x squared, like this. That's a 2 right there. And dz dy dx. And here the question isn't to evaluate this. The question is to change the order of integration. And here they've even told us which order of integration to change to. So we want to change the order of integration to be a triple integral over the same region Q of, and here they want this in terms of dx, then dy, then dz. So notice your boundaries of integration need to change as well because the order has changed. So the first thing we want to do is we can go ahead and give ourselves an idea as to what this object actually is by a sketch. Sketching these wouldn't be difficult. They're the same kinds of sketches that we've seen since the very beginning of the last chapter. We're just sketching things over a solid, over a flat region, over the XY plane. So let's start off with that. So this is not in the XYZ coordinate system. This is just in the plane. Notice that I have my x value is bound between 0 and 2. Okay, well that means that the furthest left I ever go is 0, and the furthest right I ever go is going to be 2. Now my y value is bound between 2x and 4, which means that the highest y value I ever get is 4. Now remember, the x value is from 0 to 2, so from here to here. And the smallest y value we ever get is the line 2x, which passes through the origin and has a slope of 2. Okay? So this region is what we mean when we say this right here, when x is bound between 0 and 2, and when y is bound between 2x and 4. All right, just like that. Now, we have this third set of boundaries. Now, this third set of boundaries is going to exist over this region. So if you can imagine the XY plane, you're going to have a third coordinate axis coming straight up out of this. Right? Imagine you have an aerial view here. X, Y, Z is coming up toward you. X, Y, Z is coming up toward you. And from here, we know that our object, whatever it is going to live over this region. It's going to be up here somewhere. We just have to figure out exactly what it is so we know how far up to go. All right? So from these boundaries, we know that it's going to have a minimum value of 0. So Z is going to come down to the XY plane. So really, we only want some stuff that's over the XY plane. It's never even going to retreat away from us. All right, so let's see what this surface is. All right, the upper bound on Z, the lower bound is 0. The upper bound on Z is given by Z equals to the square root of y squared minus 4x squared, which, of course, we can square both sides to make things a little more recognizable. We can write this as z squared is equal to y squared minus 4x squared. And here we can go ahead and pass that over to the other side, and that'll give us 4x squared minus y squared plus z squared is equal to 0. Just like that. You may or may not recognize this. That almost looks like a sphere, doesn't it? But not quite because of that minus. Also, a sphere would have a radius, or it wouldn't just be 0 there. Note what happens if you consider its traces. Right? If you take the xy trace, you say, well, that's just equal to 0. Well, yeah, but notice, if that's equal to 0, you can pass the y to the other side. So that's going to give you 4x squared is equal to y squared. Okay, so I can take the square root of both sides, and I get 2x is equal to y. Now, it should be plus or minus, but of course here we don't care about anything negative. So here, what this is going to be is the xy trace is simply going to be a line. Same thing for the yz trace. That'll be a line of slope 1. If I move this over to this side, I get z squared is equal to y squared. If I take the square root of both sides, I get z is equal to plus or minus y. But because I don't want any negative values, I only want this to exist in the positive region, then I just get strictly x equals to y. There is no negative there. And if I take this trace, well, I notice that's 0, right? The only way I can add 2 squares to get 0 is if I have 0. So what this gives us is I have my xy trace. All right, my xy trace, when z is equal to 0, I end up with 2 lines. X is equal to y is equal to 2x. I can move the y squared over, and then I can move the y squared over to make it 4x squared equals y squared, and then take the square root of both sides. That would give me y is equal to plus or minus 2x. So here, in fact, let me even just draw plus or minus 2x. That's got a slope of 2. In fact, that's this line here, isn't it? Okay, so here, clearly we have the right thing. It's just we're looking at too much of it. We only want this part. If we take the xz trace, okay, well, that's when y is gone. And you notice that's just 0, 0. There's only one solution to that. If you add 2 squares and get 0, well, then they must be 0. And if we consider the yz trace, well, that means x is equal to 0. So here you could move y squared to the other side, and you would get y squared equals to x squared. Y squared is equal to z squared. Take the square root of both sides, and you get z is equal to plus or minus y. Okay, so then you either get this line with a slope of 1, or this line with a slope of negative 1. Okay, so here's an object that if I look at it from different directions, I just get a cross. But if I look at it from this vantage point, I get a single point. This is a cone, or in mathematics, this is called a cone. You might think of it as like a double cone. What it would look like physically would be something like this. Okay, x, y, and z. Here we would take the xz trace is just that point. But now if you're coming out from there on the yz plane, you have these lines of slope 1. So that would be coming out and out this way. And if you're coming on the xz plane, well, then you have this coming out this way and this way, this way and this way. And what you end up having are a couple of cones. Right? In math, we just call this a cone. But here you can imagine like 2 ice cream cones stuck together, sticking out so that they're parallel to the y-axis. Okay? So here what we want is this cone. But again, we don't want the whole thing. We only want the part of the cone that is in the first octant over this region. So putting all that together, we have the following solid, we want only over this region. Okay, that means we want only over this triangle. Here I'm going to draw 4. Here this is 2. So there's my triangle. And I want part of a cone, but only over that region. So I took this double-sided cone. I took only one of the 2 cones, and then I cut it into quarters. And there we go. So there's the object that I've described. Once you've described the object, and whether that be purely mathematical with the equations, or if you're a visual person who likes to have things drawn out, once you have that an inclination as to what these boundaries are saying, now you can convert into your new boundaries of integration. So you might try this. Pause the video and see if you can describe this object using the boundaries that you have, but instead of describing it with what we have in terms of z, then y, then x, try it with respect to x and y and z. Once you have an answer, go ahead and unpause the video and we'll see, we'll go through it together. Okay, so the secret to making this not unbelievably complicated is to notice how we built this in the first place. We started by noticing these 2 and saying, okay, if I just look at these 2, I'm working on the plane. And then I'll worry about this later because that'll put me into 3D. We can do the same thing here. We can say, you know what, let's just look at the YZ plane. Let's describe that first to give us these outer boundaries. And then at the end, we'll worry about that third variable that puts us into a third dimension. So here, all I want to do is just look at the YZ plane. Okay, so looking at just the YZ plane, well, that's Y right there, and that's Z. Looking at just the YZ plane, well, here that's also a triangle. But notice here, this triangle has this boundary with a slope of 1, right? Here's the YZ plane. Oh yeah, but the YZ plane, we're looking at the stuff that's up here. We're only looking at the stuff which is in the positive Y direction, the positive X direction, all this stuff up here. But notice this one doesn't have a slope of 2 like the other one did. It only has a slope of 1 on the YZ plane. If you isolate your Z, that Z is equal to plus or minus Y. So here, looking at the YZ plane of this object, we're just looking at this triangle, where the triangle has a slope of 1. So this is the line X equals to Y. And, oh, yeah, I'm looking at the wrong side here. I don't want this part. I want this part down here because I want the part of the triangle that touches the Y axis. Here it doesn't touch the X axis. So I actually wanted this one down here. So that's going to be this triangle here. Notice if you're following along the Y axis, it starts at 0 and goes out to 4. So that's 0 and that's 4. And that's the line X equals to Y. So now I can describe this part of my boundary, but now instead of with respect to X and Y, I can do it with respect to Y and Z. So let's see what that's given us so far. Now we have the triple integral. And we're doing this dx, dy, dz. Starting from the outermost, our z. All right, well, that's nice and simple because z has to be described using only constants. All right, here's your y, here's your z, and z goes from a low of 0 to a high of 4. All right, this is my z-axis. I just copied it from over here, and that's going to go from 0 up to 4. The y value is also reasonably straightforward to describe here because we're not in 3D. This is just a plane. Here, the y value goes to a maximum of 4, and the minimum is given by this line. Okay, so you start from y equals to x, and you keep going until you get y equals to 4. All right, here's the left side. Here's the left bound on this region. Oh, it's variable. And in fact, it's y equals to x. Here's the right bound. Oh, and that's just a constant. It's always a perfectly vertical line at 4. Okay. Finally, now we have this region. Okay, by the way, this region here in red would be this region over here on the YZ plane. So now all I need to do is say, okay, well, my object lives from here coming out. Okay, well, if it lives starting from here, well, that's the YZ plane. That's when x is equal to 0. So here, this bound must be 0. And the only thing I'm missing now is how far out does this come out to reach this outer edge of this cone. All right, it starts at 0 on this flat plane. And now I just want to figure out how far is it to get to the outer edge of this cone. But you don't need to figure that out because that's already given to you. You know the equation of the cone. Here, you're simply trying to describe it with respect to the x variable. Oh, okay. So if I know that that's the equation of my cone, I can solve that for x. I can go ahead and move these over here. So that'll give me 4x squared is equal to z squared minus y squared, just like that. And now I can divide both sides by 4. So this will give me, let's see. This will give me x squared is equal to z squared minus y squared over 4, just like that. And I'm realizing I wrote this wrong. Here I wrote this as x equals y, but this is on the yz plane. This should be z equals y. So here this lower bound is from z up to 4. Yeah, my apologies. I had that written right here, and then I just fell into the default of, x is the usual variable that I use. This is on the zy plane. So here y goes from z up to 4. Okay? And so here we have the square root of both sides, and so that gives us that that x is equal to the square root of z squared minus y squared over 4, and that must be our final bound. So that's going to be now, this could be plus or minus, but of course we don't want it to be minus because here we have everything in the first octant. So here that's going to be the positive square root z squared minus y squared over 4. Oh, and I realize my signs are backwards here, aren't they? Here, if I move this over this way, that negative y squared should become a positive y squared. This positive z squared should be a negative. So here my signs are backwards. So this should be minus z squared plus y squared over 4. So let me go ahead and write that out nicely just to make sure we've got it all. That's the integral from 0 to 4 of the integral from z up to 4 of the integral from 0 up to the square root of, here let me write this with the positive one first as we usually do. So y squared minus z squared over 4, like that, dx, dy, dz. And that is our result. Whether or not you draw these is up to you. Some people are more visual than others. However, the pattern of this is as follows. To change your boundaries of integration, you want to use just the outer two to consider a projection. Your object is in 3D, but you want to go ahead and imagine what it looks like or describe what it looks like, even if you don't have a visual, on one of the planes. In this case, the XY plane. Once you have that, then this simply describes a height. It describes an extra dimension outside of this flat plane. So now once you have that described, either with equations, with pictures, or both, then we project into the new plane. Here, we don't really want this outer plane to be the XY plane. We want it to be the YZ plane. Okay, so if we want it to be the YZ plane, take this object that we had described before, and now instead of projecting it onto the XY plane like we had, now let's project it onto the YZ plane, which I did here in red. And now that YZ plane, that projection can be described to give you your outer two boundaries, and then your innermost boundary is simply whatever's left over of your function. Here we say, okay, we already knew how to describe your surface. All right, this one's with respect to all three variables, x, y, and z. In this case, z is equal to a function of x and y. And so all we have to do is to isolate the remaining variable. In this case, since you're trying to write this with respect to x, okay, well, this is z is equal to square root of y squared minus 4x squared. Okay, let's get that x by itself to figure out what that upper boundary has to be. And of course, unlike me, make sure that you don't screw up simple arithmetic here. My apologies, I did have those signs backwards. We subtract this to make it a negative, and we would add it to have that be positive. All right? And this does give us our final result. And that is it for the section. So as an exercise, go ahead and try sections 14.6. Do 1 through 33 every other odd. And that will suffice. If anybody has any questions or problems, please contact me, reach out, and I will do my best to help you with what I can. And I hope you all have a nice day.